In this video, we're going to take a look at how we can relate wavelength, frequency, and energy to transition metal colored complexes. So to start off with, we need to revisit the color wheel. So remember, for a substance to appear colored, certain frequencies of light in the visible region of the spectrum must be absorbed. So the color that the substance is going to appear to the observer is going to be the complementary color to the light that's absorbed. So if something appears blue here, then it will absorb orange. Or if it appeared orange, it would absorb blue. And so we can actually relate this to our different frequencies or wavelengths or energy of light in order to do some calculations with it. So let's remind ourselves first that d orbitals will split in a complex ion. So recalling that if we just had the transition element itself, the d orbitals are degenerate, but when we create a complex ion, we get this splitting of d orbitals into two different groups. And so the difference in energy here between the split orbitals allows electrons in the lower orbitals, so ones down here, to get promoted into higher orbitals. This can happen when the complex itself, it absorbs light with a wavelength corresponding to the energy gap between the non-degenerate orbitals. So we need to meet this energy in order to promote them up to the higher levels. We'll have a wavelength corresponding to that, and the color observed is going to be then the complementary color to the color that's absorbed. So the larger the splitting of the d orbitals, so the bigger this gap gets, the higher energy we would need in order to promote that electron. So for larger splitting, the light's typically going to have a shorter wavelength, and it's going to have a higher frequency. Now remember, we do have relationships between wavelength, frequency, and energy that we can use to do some calculations here. So let's take a look at those. So we've got two relationships here. The first is relating the speed of light, which is 3 times 10 to the 8 meters per second, is equal to the frequency in seconds to the negative 1 times wavelength in meters. The second one is our energy in joules is related to Planck's constant, which is 6.63 times 10 to the negative 34 joules per second, or joules times seconds, sorry, and then frequency in seconds to the negative 1. So how do we use these equations to solve problems related to complex ions? Well, let's look at this example here. We've got the color of a copper chloride complex ion here is equivalent to visible light with a wavelength of 647 nanometers. We want to calculate the energy gap of the split d orbitals in this complex ion. Now, we first need to recognize that if we have the color corresponding to 647 nanometers. It's appearing reddish orange, but it's absorbing on the opposite side this blue-green frequency here. So we need to use this one in our calculations in order to figure out the energy. So first of all, we need to get the frequency of light in order to calculate the energy. So let's start there with our C equals frequency times lambda. And so we've got 3 times 10 to the negative 8 meters per second is equal to frequency times the wavelength, which is 491. And we need to put this in meters, so times 10 to the negative 9 meters. So if we rearrange and solve for frequency, we should get 6.11 times 10 to the 14 seconds to the negative 1. Okay. Now that we have frequency, we can figure out energy by using Planck's constant times the frequency. So plugging in our values here, 6.63 times 10 to the negative 34 joules times seconds times our frequency we found in the first step. And we do that calculation. That's going to give us 4.05 times 10 to the 19 joules. We can just leave it in joules here, that's fine. So it's going to take 4.05 times 10 to the 19 joules of energy to promote those electrons to that higher set of d orbitals. So this is our energy gap here. So that is how we relate colors of complex ions to wavelength, frequency, and energy. That's it then for this video. We'll see you in the next one.